All right, so just because I'm going to cover things where I don't, even though I know pretty much all of you now, I don't know how you stand on this. So a couple questions. How many of you are comfortable reading assembly code? Okay, so we have some people who aren't quite as comfortable with assembly code.
Sorry, which processor? Which kind of model? Like which kind of? How many registry? How many?
For assembly code, you'll have. For assembly code, you're looking at the Apollo AGC, specifically the Block 2 module.
I'll make it up as I go.
For the machine code, it's going to be the 1802.
Okay.
Oh, okay.
Only byte code.
Okay.
Huh?
Does that have the SIMD extensions?
No. The next thing is I want to make sure that y'all are comfortable talking during the talk. So if I could get some heckling going, Alan, can you give us a heckle? You can do better than that, Alan.
You look bad.
Thank you. All right.
No one would ever move that game into that register. Come on, man.
Should I go get some guacamole?
So we're going to be going over some weird stuff. This talk was previously given at RubyConf, but I've changed it a bit so that it's more focused on this and less Rubious. Y'all know who I am, so we can ignore that. All right, how many of you can remember that time when NASA had a real expensive satellite crash into Mars because part of their program was in pounds per second and another program was in newtons per second?
Yep.
Yeah.
I remember that.
All right. So everyone likes to make fun of that, except here's the thing. How many of you have ever written an incredibly large project with multiple corporations all cooperating over hundreds of page specs and not gotten a single bug in it? Now in their case, they did have a bug. It was an external vendor who got the units wrong. Everyone else had gotten it right. It just happened to be that, you know, we all have bugs. Their bug just happened to crash millions of dollars in the atmosphere of Mars, which is like not a great situation because it takes years to get there. However, like this isn't like they really, I mean, they screwed up, but it's like this is a really relatable thing. We all make mistakes, just it went bad in that case. Some of you may not remember when we first launched the Hubble Space Telescope, it got up into space. We'd spend a lot of time getting this thing ready. We'd spent a heck of a lot of money putting this thing up. We pointed the sky, we opened up the lens, we took our first pictures, and they were all really blurry.
It's hardware problem.
And the reason why it was blurry was because they had gotten the shape of the lens wrong.
The software worked.
Yeah, well, I mean, worked as much as any software does. What's interesting about this story, though, is that because they were able to measure those photographs with Hubble in space, at temperature, orbiting the Earth in a microgravity environment, they were able to measure how far off that lens was from what they wanted. And they were actually able to get the images sharper than they would have if they had just initially gotten the number right. Because on Earth, you know, they have to make certain assumptions about how that mirror is going to be shaped. When it is at temperature in space with the sun beating down on one side, the emptiness of vacuum of space on the other side, in the microgravity environment, we can't simulate that terribly well in space. So even though this was a bug and it caused a lot of problems, in the end, it was a very expensive way to get a sharper image, but they were able to get a sharper image because of what they could learn from it. Yep?
Are you saying the images were photoshopped?
No. But another time we should talk about the colors in all Hubble images because that isn't what you think they are. It's really weird. It's not fake. It's just, it's an interpretation of a reality, but we don't have time to get into spectrometers, whatever. So today, we're gonna do 4 different stories besides those about instances of bugs and problems in space programs, because I think that we have a lot that we can learn from what went wrong. Usually in talks, we talk about things that went well, and it's awesome, and it's great, but oftentimes things that go well or become popular just happen to get lucky, and they just happen to get popular. So you don't know, like, are there the lessons that we learned in it? Are these things that they actually did well, or just things that happen to be there in a popular thing? With bugs, we know it went wrong. We know that there's something bad, so we can definitely learn from it. And even though programming is relatively new, we have been writing software bugs for decades now. So we have a lot of lessons that we can learn from.
So that font makes me think that the title of the slide should have been "The Game Goes to Space."
Why is it not surprising?
I'm going to tell you right up front, as you all know, I'm not some guru on a mountain. I can't give you the answers. So even though I'm going to be editorializing a little bit in this talk, I want you to be thinking about how this stuff can apply to your work and what you do and what you can take away from these stories. I'm just a workaday developer like you. I just happen to be crazy and spent time reading Apollo guidance computer source code. But I did this so that you can learn from these stories and kind of glean from it whatever you want and take away whatever you want. All right, so first story. We've probably all heard the phrase, you can send a man to the moon, but it's usually like the fax machine is broken. We can send a man to the moon, but we can't get a fax to work properly, which I don't know why I thought of fax. No one uses fax machines anymore. We can send a man to the moon, but for some reason, printers always get jammed in that problem. But here's the problem with that statement. We could send a man to the moon, but we had tons of bugs and engineering mistakes along the way. We got them to the moon, but it didn't all go perfectly all the time. And so we're going to be talking about the main moon mission that everyone thinks of when they think of something going wrong. That's right, Apollo 14.
What?
Okay, it's not Apollo 13. Apollo 13 is interesting, but there have been lots of movies and things talk about that. We're going to talk about one specific bug that happened in the Apollo 14 mission because I think that it's more interesting in a lot of ways, and from a software perspective, it's not all that nasty hardware stuff. There's actually a software bug, and there's some cool stuff we can learn about this. All right, so Apollo 14, they made it to the moon.
Did we really go to the moon?
Yes. That's a dumb question. There are very few dumb questions except for moon phase. It was less than 4 hours before we land, and someone on the ground noticed that the abort flag, the abort bit, was set in the computer. Now there's a problem, because the abort bit is what gets checked during the landing procedure to see did someone push the abort button. And someone pushes the abort button when they want to stop the landing and abort. Now, no one had pushed the abort button. So what was theorized was that there was a little loose bit of solder or metal inside the abort button that was just floating around in there, and every so often it happened to short out that button and act as if it had been pushed. Now, the reason why they have been fine is because the abort button isn't checked very often. That flag isn't checked very often. However, it did get checked during the landing procedure. And it's really expensive to send someone to the moon, so they only send enough fuel to land once, which means if that little bit of solder happens to short out the pin right when they're doing the landing sequence, they were going to be in big trouble because then the landing would be aborted and then they're not able to land on the moon because they don't have enough fuel to try multiple times. This is a serious problem. So it is, you have less than 4 hours before you're going to land on the moon. You have been told as the developers of this software that you need to fix this with less than 4 hours to go. You need to come up with a solution to somehow convince the computer to ignore that abort flag. You need to test that solution, send it over to Houston. Houston needs to test that solution. Then they need to send it up to the astronauts with the procedure, have them go through it, and then solve it. This is a hard problem to solve. It's especially hard because the Apollo guidance computer doesn't work like a computer like we're used to today. Today we'd be like, okay, we're just going to create a code patch. We'll send a patch version of the code that doesn't check the abort flag, and then everything will be fine. The problem is the compiling process for the Apollo guidance computer is a little different than the compiling process today. You would write up all your code. You would then take it and compile it into machine code, get all the bytes as to what actually need to be stored on the machine. You would then send that over to, I believe, Massachusetts, to the Raytheon Corporation, where they would take that byte code, feed it into a computer that then would direct two people to thread a needle through a series of small ferrite beads to literally weave the binary for the source code.
Wow.
Yes, so this is read-only memory that actually gets woven by two people by hand with the assistance of a computer telling them where to go. Then when that's done, they can then fold up all those wires, seal it in epoxy, and then go ahead and test it by adding the machine. So if we were to recompile the code, we could do that, but it would involve going through all that process, which takes a long time. We'd then need to take that source code and send it to the moon, and then have them reinstall it in 4 hours. This is not going to happen. However, they had a couple of advantages. So this is actual Apollo source code. Specifically, this is from Apollo 11, but I believe this bit hadn't changed by Apollo 14. So for those of you who aren't as familiar with assembly code, over here we have a label. So even though it's 10, 11, it's just a string. This is a point in the code that you can go to. Some of them are used to go to labels. Other of them are just used to kind of add comments about what each part of the code does. Then we have the operator, also sometimes called the mnemonic. This is a couple of character string that gives you a command. This is the operand, the thing that command will operate on. You only get one operand per operator, or sometimes you use none. And then over here is a comment, which, hey, they still use hashtags for comments. That's kind of cool. All right, so the first thing that this line of code from the computer does is it calls the CA command. This clears out the accumulator, one of the registers in the machine, and then pulls in whatever the operator is. So this will clear out and add this flag word number 9. This is a word in memory that stores a number of different flags. We then call the mask operator, the mask operator, and specifically we're going to mask it with this let abort bit. So this is going to mask out that word so that only the let abort bit is left. We then have to call the extend command. We don't have time to go into what that does. It's just magic under the hood in the machine. I don't actually fully understand what this command does, but it's something to give them extra commands in the machine with a limited address space. And then finally, we are going to call a branch if 0 command essentially. So we're going to check, okay, we have taken this word, we've masked out to 1 bit. We are going to branch if that word is 0. So if that bit is set, we are not going to branch. If it is not set, we're going to branch. So specifically what this code does is it checks a bit in the computer to say, is there this let abort bit set? If that bit is set, we are going to skip past this whole check the abort button sequence because this is not a part of this is not an area where we care about the abort. Such as when you're orbiting the moon. You don't need to abort orbiting the moon because you're just sitting there in orbit. So here's the solution that they first came up with. Just set the let abort flag. You can manually go in with the Apollo guidance computer, set any bit in memory. So if we go ahead and set that bit and just tell the Apollo guidance computer, hey, you're not in an area where you need to care about aborting, because look at this let abort bit. This is not an area where you can abort. Everything's going to be fine. The problem is that the landing sequence sets that let abort bit to 1. So as soon as they enter the landing sequence, that let abort bit gets set. You can then manually go and unset it so that you are no longer checking the abort flag. However, if in between the time the computer set it and the time that you reset it, that little bit of solder happens to hit, you're screwed, mission aborts. All right, so the actual solution ends up a bit complicated. We have the code that we saw before, but then immediately after that, we have this next section, which is what it is P71 now is checking, are we in program 71 now? So the first command here, is going ahead and doing it's clearing out the register like we did before, except this time it's subtracting away a number. It's subtracting away specifically this mode reg number. And what mode reg is that is a area memory which is storing what program are we currently running. We're then adding in a magic number to it. Then we're calling the extend command, and then we're branching on 0. So what this bit of code does is it copies in whatever program we're currently running, and then checks, hey, are we running program 71? If we're running program 71, go ahead and do the same thing that you would have done with the let abort bit. Just go ahead and skip around it. Because program 71 and program 70 are both the abort programs. So what this bit of code does is it checks, hey, are we in an abort sequence? If so, don't run an abort sequence because we're already in an abort sequence. And that would be bad if we tried to abort twice and then the rocket engine is flailing about doing all sorts of bad stuff. All right, so here's what we can do. Instead of setting the let abort flag, we can go ahead and just tell the computer, hey, don't worry about it. We're already in an abort sequence. Then do your landing with the computer thinking that it's in an abort sequence. Then everything's going to be fine. However, it is a little, yeah.
Can you go back to slide I'm curious about something?
Yeah.
The one DEC 71, is the 71 there program 71 or is it just coincidental?
Here's the problem. I don't know if it is hex. or if it is a mask specifically designed for checking whether or not it's
Or is
71.
the December 1st of 1971? I'm just saying, I guess.
So I thought it might be that, and I thought it's got to be hex, right?
It's a map.
It's either hex or a magic number. I think it might just be the variable name for a magic number.
Okay.
I need to dig into the source code a little bit more to figure it out. It's also confusing because they're doing subtract instead of add, and then they're adding another number into it.
Right.
But I assume there is some reason why. But we're dealing with, bit bashing here, so.
Well, and like you say, it says P71 now, so I wonder if the 71 is referring to a P71 or not.
Yeah.
Okay, I'm sorry, I just wanted to ask you that before you got away.
Okay. So the problem is that mode red flag, or that mode register bit, that actually, you can't just set it to 71 because the computer actually checks what program it's in the middle of the landing sequence so that it can go ahead and set itself up properly. So the sequence they came up with was this. First, you set that mode register to say that you're in program 71. Tell the computer, we are currently in an abort sequence. You should not abort because we are currently in the abort sequence. That's the program that we're running. We're not, but you lied to it. Then you go ahead and wait for ignition to happen. The ignition sequence is going to automatically set that let abort flag. So it is going to say, hey, if an abort happens to come, you should set it. However, it'll ignore that because we're saying that we're already in an abort sequence. Then you need to push the throttle up to full. You then need to go into memory and set a thing called the zoom flag. We don't have time to go into that, but it's just another flag that you have to set so that the computer will go, okay, I may not be, or I'm in program 71, so another bit of code didn't hit, so the zoom flag didn't get set. So we're going to manually set it to convince the computer that that program actually ran, even though it didn't. You can then go ahead and reset the abort bit because there's no other part of the landing sequence that's going to set the let abort bit. You can then restore the program, the mode register, to program 63, the program that you're actually in, so that the rest of the landing sequence can run knowing that it's actually the proper sequence. Then you go ahead and pull the throttle back down to 0. Now the computer can take control of the throttle. If you're confused, don't worry. It is a confusing sequence. It took me a long time to read through this and figure it out. But this just shows how many hoops that they had to jump through to be able to convince the computer that it should not abort.
That's hell yeah, actually.
Now, as far as lessons we can take from...
Sorry, to interrupt you. That actually is decrement 1 on 71. That is decrement, basically. It's a label later on. That is decrementing by 1, 71. Anyway, sorry, go ahead.
Okay, so they're subtracting by 1 and then decrementing again.
Yeah, there's also 1 deck 70 as well. Anyway, forget about it. Keep going.
Yeah, so the reason why they have 1 deck 70, that's the other abort sequence. What I'm not showing you is there are 2 beats of code that are exactly like this. One that checks that they're in 70, one that checks they're in 71. I think they picked 71 just because it was the first one in the program, but whatever. If you ever want to spend time reading Apollo Guidance computer source code, it's great. There are actually jokes in there, but you have to dig for them. All right, so as far as lessons, monkey patching is really great. This saved people going around the moon. If their computer was, if they couldn't go in and manually edit the memory underneath the computer and trick it into doing things that it was designed specifically not to do, all these checks were designed to make sure that all this stuff didn't happen. If they weren't able to do that, then they may not have been able to land on the moon. It would have been a crapshoot. So monkey patching is awesome. If you are always writing all your programs so that they are totally ironclad and they always do exactly the same thing, you are assuming that you didn't write any bugs in there. And at some point, you'll have to go in and fix things. And if everything is too tightly coupled around your assumption of what's correct, that will cause you problems. I will, however, say that monkey patching isn't really that helpful. Most of the time, it's only helpful in special situations, and usually you do want a really ironclad program, especially because they didn't have to do with hackers trying to break into their thing because they were around the moon. But it is cool that they were able to fix it, and the only reason why they were able to fix it is because of this. I'll also note that they did, after this, add a program in there or a sequence in there to allow them to just say, hey, should the abort button break in the future, let's just give a quick, easy one-button way to say, hey, just ignore the abort button from now on. Let's not hop through this.
What if that button breaks?
Well, it wasn't a button, it was a software sequence.
Do you know if there's ever a time when they would want to abort during landing?
Yes.
Because if they did this and then needed to abort, they wouldn't be able to abort?
So they wouldn't be able to abort by going to the abort button. However, they did come up with an alternative solution, which was, okay, they got to ignore the abort button. However, the abort sequence is just a program, and they can manually go and type the computer. It takes a little bit longer, but then they can go ahead and do that. And you're going to want to do that because orbital mechanics is hard, and getting yourself to launch back into orbit. If you've ever played Kerbal Space Program, this shit ain't easy. All right, next thing. How much damage can one line of code do? The answer, a lot of damage. Specifically, we're going to be talking about the Ariane 5 Flight 501. The Ariane 5 is currently one of 3 operating heavy launch vehicles. Those of you who are into SpaceX, theirs technically aren't heavy launch vehicles yet because they haven't launched anything heavy enough. Heavy launch vehicles are the things that can do things like lob 20 tons of stuff into orbit. That is a lot of stuff. These are big, honking rockets. We don't use them as often as other rockets because it is really expensive to run them, but when we want to shove something big in space, these are the things that we go to.
Like an ICBM?
No, those are pretty small.
Sorry.
If you have a 20-pound or a 20-ton nuclear warhead, my God, what are you doing? Well, I mean, you're going to destroy a city, but then, like, it's just rural area around that. It's not very efficient either. But, like, let's not get into nuclear weapon design. All right, so the European Space Agency in the early 1990s was building the Ariane 5 rocket. This was a successor to the Ariane 4 rocket, but wasn't necessarily built on top of it, though they did borrow some components from it.
Wait, hold on, what era are we talking? What time?
1990s. Early 90s, I think. All right, well, it started development in the early 90s, then went into the late 90s, I think.
Okay.
This project took maybe a decade for them to do all the design work. I mean, there's a lot of like pre-planning stuff that goes on, and it's estimated that this cost $7 billion. That's not just the cost of the rocket, but all the planning. However, these rockets are insanely expensive. And not only are they insanely expensive, they're not reusable. Like most rockets, you shoot them up and then you're done with them. So you really have to hope that they work. All right, so Flight 501 was going to be the first flight of the Ariane 5 rocket. However, it also had an actual payload on it because they were relatively good at rocket design. They had designed a lot of rockets, and this is a big expensive thing, so instead of just doing a bunch of test flights, why don't we design everything really carefully, spend a lot of time on it, and then have our first flight be an actual commercial flight to actually launch real things into space. Overall, the launch was relatively nominal. There were a couple of small issues that happened in the hydraulic system, but everything else was fine. Weather was relatively good. Everything seemed to be going fine. Less than a minute into the launch, however, the thrusters on the rocket gimbaled to one side as far as they could. That meant the fiery bits shoved over to one side and caused the rocket to veer over to one direction. This is bad because the pointy bit of the rocket is pointy so it can cut through the air. And you want that pointy thing cutting through the air. If it starts to turn too far, all that wind starts hitting against the side of the rocket. Rockets are made to be strong where they need to be strong and light and really flexible everywhere else. So when all that air started hitting the side of the rocket, it fell apart. It started to fall apart, all the bits were falling off of it, and then it exploded. A committee was formed to investigate this, and they did find that the explosion was in fact a good thing. The rocket had, as designed, detected that it was falling apart. Specifically, I believe that the booster thrusters had fallen off the sides. It detected that and realized, hey, I'm a big bomb that's about to fall to the ground in Africa. This would be bad. So I'm going to blow up in the air so little tiny bits of flaming rocket fall to the ground as opposed to big explosive rocket falling to the ground. So the explosion was a good thing, which is rarely the case. However, the committee eventually, after a lot of work and going through the code, managed to figure out exactly what had gone wrong. And what had gone wrong is this line of code. I don't know how to read Ada code because no. It also is really hard for me to figure out, is this written in English or in French? Because either are really possible. because for some reason low-level programmers love really long, non-descriptive variable names with a lot of things in them. But what this bit of code did is it ran on two of the gyroscope computers, the things that help sense the rocket which direction is up. And specifically, this value right here overflowed. What happened was they had a 64-bit float and they converted to a 16-bit integer. 64 is bigger than 16. So it overflowed. Now, luckily for them, they had two of these computers running inside the rocket. It was a redundant system. And initially, this overflow happened in the backup computer. So the backup computer failed. However, literally milliseconds later, the main computer also failed because they're running the same code and getting the same data. So of course they both failed. So it fails, but there is no backup. Now, what the computer did at this point is it sent a diagnostic message out to say, hey, I have failed. Here is the information about how it failed. It sent out that diagnostic information, and it was received by the thrusters. The thrusters do not interpret diagnostic information, they interpret thruster commands. So it looked at that message and it said, cool, this is a thruster command. It's telling me to gimbal all the way to this side. I'm going to gimbal all the way to this side. So it did exactly what it was designed to do. All right, so the committee continued to investigate this, and what they discovered was that luckily the design team was very smart. This particular unit was pulled from the Ariane 4 rocket, but they knew the Ariane 5 had different specs. And so they went through and found every single possible overflow in the program. They had found all of them and identified them. This is great. They knew where all the problems were. They had found this specific problem. And they put guards around those overflows, except they didn't put guards around all of them because they had a limitation in their requirements that the processor could only hit about 80%, I believe, maximum compute power. So they couldn't like hit the processor 100% because if the processor gets overwhelmed, the rocket won't know which way up is and bad things will happen because we need to keep the pointy end up, so we better know which way up is. All right, so they had known about this, but they didn't protect against this one. The reason why they didn't protect against this one is because they had taken real flight data, fed it into the computer, and checked to make sure, okay, under real circumstances, will these overflow? All the ones that could overflow, they put checks around. All the ones that couldn't overflow, they didn't put checks around. So they were safe, they were good, they were doing not quite test-driven development, but they were testing with real data, not mock data. The problem is the data that they were testing was from was the Ariane 4 rocket flight data, not the Ariane 5. And they built a different rocket so it could do different things. And it happened to tilt over a lot faster and a lot more, thus the number was going to get larger, thus what caused the overflow. So they were
like a test versus types argument for all versus exist.
Right. So in this case, type system wouldn't necessarily save them because they knew that this would have overflowed. And test wouldn't necessarily save them because they had tested it and they had tested with realistic data. The problem was more of a systematic problem. And so the committee ended up coming with a number of suggestions, and I've sort of boiled out some of these recommendations. One is that they had protected against random faults. They were running a dual redundant system. They had two computers going, so if one randomly failed, they could switch to a backup. However, they weren't protecting against design faults. They had assumed, essentially, that if there was to be a failure, it would be a random failure. It wouldn't be a failure in something that they had intentionally written that way. Which brings us to the next advice. They said that they were assuming that the software was going to be correct. The committee recommended, assume that all software is faulty until you can prove that it's correct. The burden of proof is on the person who wrote it. It's not on the people who are testing it. This especially showed up in the fact that that computer really shouldn't ever have sent out an error message. Why would you send out a debug message when there's a fault? You are a rocket that is currently launching. Try and do a best guess of what you think it might be. You know, you can like at least try and guess which way is up and do your best job to do it. You may limp up to orbit, but at least you'll get there or not, you know, catastrophically fail. And a lot of their systems and test procedures were designed around assuming that the software was correct, as opposed to just assume everything is broken and try and prove that it is good, and only actually run it when you can prove that everything is actually good. Yeah?
But the debug message is not supposed to go to the ground station somewhere too, or did it just happen to get received by the thrusters?
No, so so it did get caught by other systems, but the debug message, I believe, was in there so that when they're doing testing on the ground, it would basically like, oh, it failed, this is bad, we never want to see a failure. As opposed to the Erlang way of doing it, which is, hey, failures happen all the time, so we should just deal with that as a normal part of programming, as opposed to, let's do the kernel panic thing and just freak out and shut down.
That's a bit tangential, but does that mean there's kind of some bus that they're all talking on and they can all see each other's stuff?
They weren't all on the same bus, but I mean, I didn't look into it this closely, but the two units had to be connected because the gimbals had to be connected to the things that would direct the rocket thruster.
If I remember correctly, A2FP operates on like a message bus kind of system.
Right, but it's important to know that there were a lot of computers running in the system, and these were just two very small ones. Yep.
So are you saying like desktop software developers were developing the software for this aeronautics?
Oh no, they were professional software. Like if you read the committee's notes, and it's an investigation committee commissioned by the European Union, so it's not like the most thrilling read, but there's a lot of good stuff in there. And they did say like these were really good professional developers. The problem was not
aeronautics.
They were aeronautics developers.
Really?
Yeah, no. So all their stuff had worked before, and they are really good at their job. It just this happened to highlight a couple of bad assumptions that they're making in a few of their processes. But I mean, well, we can get into it later. They are really good developers.
Okay.
I can tell you, it's interesting you bring up Area 5 because the programming language Eiffel came out of that. Bertrand Meyer based his programming language, which has preconditions and postconditions that are checkable, out of that failure.
And there's a good write-up by the people who did Eiffel analyzing this, and they do analyze it, saying like you could say like, oh, the problem is they didn't check for overflow. Oh, the problem is and I think it's the authors of Eiffel, but they did a really nice write-up saying like you can look at all these people did a good job. They really did good. There were some language design things that caused that issue, which Eiffel tried to solve, but also some process issues, which is how the committee recommended solving it. Because if you're a rocket manufacturer, you're probably not going to want to design a new programming language.
Was this a manned rocket? Is this a manned rocket?
No. These are heavy lifting rockets. There have only been 2 heavy lifting rockets, I believe, that have been manned, really. That's 75 and Space Shuttle. Because, we don't. I mean, this is just for sending satellites into space. Yep.
And then again, I'm not that familiar with the requirements in aeronautics, but when it comes to nuclear, there's always a backup or alternative in case the primary should fail.
Right, and so
I don't know if aeronautics incorporates that. I mean, I would.
So they had that. They had 2 copies of these computers. Most systems operated in duplicate. However, that only protects you against random faults. This was a design fault. So if you have 2 duplicate systems and they both will fail under the same conditions by design, then they're both going to fail. That won't save you from anything. Though they do still use duplicates because that's really important. Yeah.
Is there much use of like people writing like individual clean room implementations of the same thing to guard against those kind of design flaws?
What do you mean?
I want to implement this algorithm. We'll have 2 different teams do the same thing, implement on 2 computers, and if they disagree, then there's a problem. Then that's at least a defense against one design flaw.
The problem is that gets really expensive,
Sure.
and they are basically hiring outside contractors. This specific unit was pulled from the Ariane 4 rocket, and they knew that there were going to be some problems, which is why they checked it. But I mean, this is old software that was assumed to be good because the Ariane 4 rocket was a good rocket. It launched.
Yeah, I'm just curious if it gets used also.
The next thing I said is don't just focus on code, also focus on documentation. They wouldn't have been able to find out a lot of these issues and a lot of these processes and a lot of things were discovered unless they had all this really good documentation that they did of a lot of their stuff that they recommend that they could do better. But I mean, like, if you were initially investigating this and you didn't have documentation about the process and what had gone on, you would look at it and say, oh, you guys just didn't check that there was an integer overflow, morons. As opposed to seeing like, yeah, they did check it, and they knew it, and they tested it, and they made sure that it worked. There were some other issues that they had with the hardware processes, but whatever. The final thing is the saddest part of all this. So that particular bit of code that failed, that caused this issue, what that bit of code did is it calibrated the gyroscopes when the rocket was on the launch pad so that it would know what direction was up. And it continuously calibrated it while it was on the launch pad up until launch, so that as soon as they launch the rocket, they have a really good knowledge of what direction is up, and they're like really up to date and good with their calibrations. The problem is, why is the thing that checks what direction is up running while you're launching, moving and not always facing up? Why are you running that calibration sequence? Well, the reason why is they had problems in the past where they would launch previous rockets using this unit and similar units. They would do a launch, except the launch would be delayed. And if the launch was delayed, they had to restart all these calibration programs and restart all these systems, and then delay the launch even further, which can potentially cause problems because you can only launch at certain times, and also it's very weather dependent. So they were very clever. They said, okay, we have this calibration sequence. Let's just keep the calibration sequence running like 40 seconds after or whatever. That way, hey, if the launch happens to get delayed, we can then, the calibration sequence is still running. We can pull from it. Except while you're launching, that calibration sequence isn't needed. How much harm can a little dead code do? A little code that doesn't need to be running? How much harm can it cause? Explosions, badness, all sorts of things. So their final recommendation was like, if you have code that doesn't do anything, please do not run it. Remove it where possible. Like, we treat dead code as if like, oh, it's dead, so it can't do any harm. But there are a lot of security bugs that have happened because there's a little bit of dead code, and don't worry about it. Nothing will ever hit that until someone figures out how to hit it, and then hell breaks loose. No. Google has some nice stuff recommending that. So, as a postscript, I would like to note that the Ariane 5 rocket, even though its first launch was less than successful, was overall a very successful program. Their last failure was in 2002, and they have subsequently have, I believe, over 80 consecutive successful launches. So this is a really stable, really reliable platform. They did have this bug, and they did make some mistakes, but they engineered a really fantastic rocket that is still being used to this day. This is a rocket designed in the 90s that currently there are planned launches into the 2020s. So like this is a good thing, and they solved this and they fixed it, and so high fives to the ESA. All right, so next we're going to go to a slightly different place. We're going to talk about rocket design in the USSR back during the space race. Now we all know that the US won the space race because we're Americans and we're the best. Those of us who aren't Americans know that we Americans are the best and we won the space race. And why did we win the space race? No, I'm being a little flippant. We'll get to that. We won the space race because we're the first people to orbit the moon and the first people to land on the moon. And to this day, we are still the only humans, or the only country to have sent humans to the moon and to have those humans land on the moon and walk around and play golf and do all sorts of other things. Maybe accidentally they did a little science too. Whatever.
But did he make the golf hole? That you know. Serious question.
Sorry, can you go back for a second?
Yep.
Another slide.
Just serious golfers. Come on.
Sorry, what is the space race? I thought it was going to the orbit.
Oh, no, so the space race. So the space race was a time in history when the U.S. and the Soviet Union were both basically competing to one-up each other to reach the ultimate high ground. The moon specifically was picked as a target at an end game because that's kind of the ultimate hard thing to do.
Okay, sorry, we're recording, so I should stop talking, just because maybe it's a renewal in a year, and I don't want to break everything. But yeah, so when you say space race, it's actually moon race, basically.
Right.
The Kennedy promise.
So that's the moon race is how the U.S. likes to think of the space race.
Yeah. Okay.
Because we like to remember how we spent a decade and we got a man to the moon. What we don't tend to remember as Americans as much, and what we don't teach as much, and we don't make as many documentaries about, is that the Soviet Union also did okay in the space race. They did a couple of things before us.
They did.
More specifically,
They launched a satellite.
besides getting a man to orbit the moon and getting a man to land on the moon, they did essentially everything before us.
Yeah.
Like every single thing they possibly could have done. My favorite there is the first mission without spacesuits. So the first, it was the first mission where they actually had a spacecraft where the astronauts inside of it could, like, not have to wear their spacesuits for safety. That, the spacecraft was safe enough. The reason why they had the first mission without spacesuits is because they did the first 3-person spacecraft. First mission without spacesuits was kind of a freebie. They wanted to beat the US to having more than one person go into space. So they designed a spacecraft, which was kind of a hacked-together version of their 1-person spacecraft, kind of. And it didn't have enough room in it to fit 3 people if they were wearing big, bulky spacesuits. So they just didn't have them wear the spacesuits because they wouldn't fit. But hey, they got to space before us without spacesuits.
Can I ask a question?
Yeah.
About the last one?
Yeah.
They took the first image of the dark side of the moon?
Yeah.
The first
Really
satellite.
big pink flood.
Because
First robot.
they got the first satellite to orbit the moon. And so they had a satellite orbiting the moon, which meant they had a camera on it so they could take a picture of the other side.
So that leads to my second question.
Yeah.
So they also took the first picture of the full globe as well, maybe, because Americans made the first picture with the Apollo 10.
So like the moonrise photo?
Yeah, that was from Apollo 10. It was the first picture ever.
I don't know if the Soviets ever turned around the camera back at Earth. Like that was like they didn't think that much. Like, hey, like a lot of the engineers weren't really thinking like, hey, we're going to the moon, let's take a picture of the Earth.
Yeah.
They didn't really see that might have been a thing. Anyways, so the question is, if the USSR was so good at beating us every single step of the way, and they blogged us in the space race, why is it that they were never able to send a person to the moon? There are a lot of reasons for this. However, the one I'm going to focus on is that getting to the moon is hard. And the hard I'm talking about here is the fact that you have to get an object that is capable of landing on the moon and returning to Earth into orbit. That means you need to launch a big, heavy thing into space. Now, there's this gravity thing on the Earth, and the Earth may not be like the biggest planet, but the bigger a thing you're trying to get into space, the harder it is. For those of you who aren't familiar with rocket science that much, there's a common issue in engineering rockets, which is you need to design a rocket not only big enough to send the thing into space, but also big enough to carry all the fuel required to send the thing into space. Because every little bit of fuel that you use to get up, you then need even more fuel to lift that fuel up, and so your rocket just gets heavier and heavier and heavier. Now, the US solved this in a very stereotypically American way. They designed the F1 rocket engine, the most powerful liquid-fueled single nozzle engine. I know that there are a lot of asterisks on there, but it was a stupidly powerful engine. It was, to give you an idea of how stupidly powerful this engine was, it needed to consume a lot of fuel, because the way a rocket works is you take some fuel, you explode it, and then you just take that explosion and direct it downwards, and then it pushes you upwards. And you just constantly have that explosion going on, unless you're using like a nuclear bomb-powered rocket, which is really weird, and the US actually tried to do that at one point, but let's not get into that. That's a fun story for another day. So you need to pump fuel. And if you want to have a stupidly big engine, you need to pump a lot of fuel. So the F1 engine, I did out the math. If my math is correct, the F1 engine could take an average-sized bathtub, if it were full of fuel, and drain it in about 200 milliseconds. So that means you have a bathtub, you blink, and then it's empty. And if you've ever waited around for filling a bathtub, it takes forever. So this thing sucked a tremendous amount of fuel so that it could get all that power. However, the F1 engine wasn't even big enough to get their big rocket into space, so they had 5 of them. They had 5 of these stupidly big, stupidly powerful engines to take their stupidly big rocket into space so that they could get something big enough into space that could go to the moon. To give you an idea, Wernher von Braun, who's standing in front of them, he's like 6'1". This is not a short man. And he's standing pretty far in front of this, but you can see these engines are ginormous. They are massive, beautiful works of engineering. The problem is the USSR as mighty as they were, they didn't really have the might of US industry. They didn't have all the manufacturing companies that the US did. They didn't have, the military industrial complex that the US did. And so they had to approach this problem a bit differently because they weren't going to be able to build such a big, powerful engine. So they took a different tack when they designed the NK33 engine. Since they knew they couldn't go big, they decided to go efficiency. So by efficiency, I'm specifically talking about efficiency in terms of thrust to weight ratio. How heavy the engine is compared to how much thrust it produces. If you have a lighter engine that compared to its weight can produce relatively more thrust, that means you're getting more thrust for every pound of your rocket, which means you can have a lighter rocket. It's going to be a little bit easier to do it. However, even though they were going to have this really efficient engine, that wasn't going to be enough because you have this really efficient engine, but it's not as big, and it's not as powerful as the American rockets. So they had 33 of them strapped to the first stage. 33, I'm sorry, 30. No, I misspoke. It was 30. I believe it was 30.
K33.
I thought it was more
30 of them.
In the first stage. It's specifically in the first. And it actually is a little complicated because
it was a lot of
So I say,
they all crashed.
over 30 engines strapped to the bottom of this thing. That is a lot of controlled explosions spewing out explosive fuel out the other end. So, in addition to being really efficient, because they had so many of them, they had to make them relatively simple and reliable. Because if you're going to have that many of them, you can't have one of them going bad. Obviously, if you have fewer engines, they also have to be reliable, but they had so many that all the piping was so complicated to get the fuel to all of them, they also had to focus on simplifying.
I thought they had some fault tolerance.
Kind of, but I mean, it's...
There's a single fuel tank that feeds all of them?
Yeah, but 2 fuel tanks to feed all, because you need an oxidizer and...
Yeah.
All right, so the US was relatively methodical in the way that it designed rocket engines. Now, a lot of this is a gross oversimplification, but the basic ideas are true. The US was pretty methodical in its design of its space program. It knew the whole world was watching them. The public was watching them. The press was going to document everything that went on. So every failure for them in the space race was a major PR disaster. So they wanted to make sure whenever they did a launch, whenever they did a test, things better have the best chance possible of going well. So they would test their engines a heck of a lot before they strapped them to a rocket and launched them to make sure that when that launch went, it would be relatively successful. And that shows in the Saturn V launches and the launches of the earlier Saturn program. They were relatively successful. They had very few, if any, real major failures of that rocket platform. They had issues in other things, but the launch platform worked because of how much testing they did. The Soviets took a more hardware-centered approach. They had the advantage of not having a free press. And they had the advantage of the massive Soviet Union so they could launch out in the middle of fucking nowhere where no one can see them. So if a rocket blows up, you just don't tell anyone about it. And when it succeeds, you inform the world about how great your engineering is. Now, this may seem like they were, just slapping stuff together and not doing a good job, but this meant that they could work in a more agile fashion. As opposed to really carefully designing everything, they would get something that they think would work, do a good job designing it, and then strap to a rocket, launch it. If it succeeds, hey presto, everything's good. If it fails, whatever, you learn from it. You then go ahead, design another one, build it, iterate until you have something that's just enough to be able to beat the Americans and beat them out because you're not spending all the time testing. Surprisingly few. A lot of these were non-managed launches. Now, because their primary goal was to beat the Americans and they had no free press, it meant that they were blowing up a lot of rockets. The N1 rocket, their equivalent of the Saturn V, the one that was going to take them to the moon, had 4 launches total. All of them blew up or fell over and blew up or barely got off the launch pad and blew up or fell to the ground and blew up. It was a bad situation. Some of them flew pretty far and then blew up. However, they only have 4 of them. By the end of the fourth one, they're like, okay, we have this NK-33 engine, which is going to be their next generation rocket engine for their first stage. They learned the lesson from the previous generation. They designed this rocket engine. This was going to be their ticket to getting to the moon. Now, mind you, by this point, the US has already made it to the moon. The moon is kind of a passé thing. Been there, done that. So, the N1 program was canceled. And the Soviet government said, okay, you designed all these rocket engines, you never launched them, whatever, that's great, just scrap them, destroy them, we don't want anything to do with this anymore.
Oh.
However, the engineers were smart. They didn't destroy those rockets, they just said, yeah, no, sure, we'll destroy them, and then just hid them away in a warehouse. And they didn't really tell anyone about it. Now, this was back in the 1960s and late 1970s. So they had all these old rocket engines stored in a warehouse. Soviet Union falls. Russia is then born, kind of. They start opening up for trade more. And the US rocket engineers hear about this rocket engine, and the Soviet Union, well, the former Soviet engineers, go out to them and say, hey, so we have this rocket engine, and you guys might be interested in it. And the reason why they thought people might be interested in it is because despite the fact that this rocket engine was from the 1960s, the NK-33 was still in the 1990s a pretty good rocket engine.
25% better.
Yeah, specifically around 25% better. It was actually, its thrust to weight ratio, that thing that they were trying to optimize for, was better than every single American rocket engine that the American engineers had tried to come up with. That meant in the decades that the Americans had been improving their rockets, they hadn't gotten a better thrust to weight ratio than the Soviets got in the 1960s. To this day, it is, depending on how you count it, effectively the third most efficient in terms of thrust to weight ratio rocket engine ever made. This is a really good bit of engineering. Part of the reason why it was so good and was able to have such impressive numbers is they had perfected what was known as the closed cycle engine. And we don't have time to get into what that is, so you can ask me about it afterwards. Effectively, imagine if you have these rocket pump, or these pumps that are pumping all your fuel. So you decide, hey, we have all this fuel from the rocket engine, let's use that fuel to also fuel the pumps, except, hey, we're burning all this fuel in the pumps, so why don't we redirect that burning fuel for the pumps back into the rocket engine and use it to, help thrust the rocket more as opposed to wasting all that fuel away. The problem is this means you have to create a pump that can withstand thousands of degrees in temperature. And in addition to withstanding thousands of degrees in temperature, you need to cool it down to deal with that, except the thing that you use to cool it down is your liquid oxygen oxidizer. The problem is liquid oxygen, though it's really cool, so it'll help cool down your engine a bit, though you still have to survive all these thousands of degrees, liquid oxygen is really corrosive because it's oxygen, like it's the definition of corrosive, it's oxygen. Corrosion is oxidization. So the problem is you're taking this really nasty stuff and using it to cool down your metal engine. The US had actually deemed this technology to be impossible, but somehow the Soviets managed to do it in the 1960s. The US was a little bit incredulous about this, because imagine if someone came to you and said, hey, I used to work in the Soviet Union, I have all these servers that I designed, they're actually more efficient in terms of watts per floating point operation than anything you've managed to come up with, even though we designed in the Soviet Union in the 1960s. And oh, you know that quantum computer thing that you guys are figuring out? Yeah, we figured it out in the 1960s, don't worry, it's like super easy, whatever. Imagine if someone tried to sell that to you. You wouldn't necessarily believe them, but the US tested these engines, and they were in fact as good as the Soviet Union was saying. So the Soviet Union managed to sell these engines to the US for $1.1 million a pop. That means that they had engines from the 1960s sitting in a warehouse that in the 1990s they could sell for $1.1 million each. That's pretty amazing. And it shows how impressive they were as engineers, and yet the USSR never made it to the moon. Even though they were capable of doing all this really impressive engineering, they were never able to beat the US in that particularly impressive feat. And there are a lot of reasons for this. While they had a really agile approach and were able to adapt and beat the US every step of the way, maybe they never really had that big picture plan. That's sort of the non-agile side of things, where you have to move slower and kind of figure things out and have the big goals in mind. They lacked good leadership. They had lots of political disputes. It was the Soviet Union, and I don't know if you've heard, things were a little rough in the Soviet Union. And they had a couple of political problems. That may have hindered them also. But for whatever reason, they didn't make it from the moon, despite all of the amazing engineering and how good they were. All right, final story for the night. We've talked about a bad line of code, we've talked about exploding rockets. Now we're going to talk about one bad bite. Just one little bad bite. And specifically, it's a bad bite in the Galileo spacecraft. Now, Galileo was a spacecraft that NASA designed, I believe, in the 1980s, launched in the 1990s, and eventually in the late 90s or early 2000s, made it to the Jovian system, explored Jupiter and its moons, got some really amazing pictures, and also did some really amazing science work. This was a very successful mission. It did a lot of really amazing things, except there were a number of problems along the way, like there were with any spacecraft, like there is with any engineering project or anything in general. They did have their issues. Now, specifically the issue that I'm going to be talking about is with their magnetometer, the thing that detects the magnetic field. The magnetometer had its own little computer in it running the magnetometer code to run the magnetometer, gather the data, process it, send it out. Relatively simple computer because, it just has to measure a magnetic field. It's not doing a lot of complicated stuff, but it's important all the same for science. What happened was, one byte in the magnetometer source code that was stored in ROM, one of the bytes in that ROM went bad, which meant that in the middle of the program, there was one byte that wasn't correct, which pretty much all programs are going to fail if a byte randomly goes bad. There are programs that won't fail, but they're really weird. That's a subject for another day. So let's take a moment to put yourself in JPL shoes with the problem that they faced. You have a bad byte in the middle of the code, so you're going to have to rewrite the code. You can, unlike the Apollo program, you can send the code up and send a code branch. The good news is you have the code, and you know what byte is bad. You know exactly what's wrong and where it is. So this is going to be relatively simple to deal with. You're not going to have to go through and figure out what's going on in the system and debug from the outside. You have the code, you know exactly where it's wrong. However, the code was written in Forth, and we'll get into Forth in a moment. Forth is a cool language, but it's a little weird. But it's relatively common in space exploration, at least compared to the rest of the world, where Forth is a program that maybe gets mentioned in a list of here are all the programming languages that have ever been developed. JPL had developed this code using a development environment for the processor that they were using. That development environment was written for the Apple II. It is the mid to late 1990s. So, JPL got rid of all its Apple IIs because it hadn't used them for a very long time. So, you have the code, that's good, but you don't have the computers that code was written on. However, that doesn't really matter because you don't have the development environment that was written for those computers anyway. So you have the code that gets compiled to the computer using a compiler that you don't have in a development environment that effectively no longer exists that you don't have access to. How would you be feeling right now if your boss came to you, said, hey, we need you to fix this problem, it's in all this compiled code, here's the source code, also we don't have a compiler, we don't have any of the developer tools or anything related to the processor, go have fun.
I'd be saying to him, how do you feel about prayer?
That's a good reaction. The Galileo magnetometer team said, this is going to be too expensive. We could spend a lot of time working on it. We could write the compiler and all the development tools, come up with a patch, test it, and fix it. So that's going to be really expensive. It'd take a lot of people because this is complicated. So this is too expensive, and we're just going to have to, say we can't use the magnetometer anymore. Enter Ron Garrett. Ron Garrett was one of the engineers at JPL. He was working on a different team on different things. And he found out about this problem, and he thought he could fix it. And he had a couple of advantages in his favor. One is the 1802 processor which was running. The 1802 processor, apparently, I just have to go off hearsay, was a relatively orthogonal processor, meaning that if you're going to write a compiler for it, a lot of the commands are very simple and very similar to each other, unlike an x86 processor where every command is its own special thing and there are 12 different ways to do everything and it's going to be really complicated. It also had a lot of registers, which meant it was relatively pleasant to work on. You didn't have to, wave things around with it. Another advantage they had is the Forth programming language. How many of you have ever seen Forth code?
Whoa.
Cool. That is good. For those of you who haven't, this is what a valid line of Forth looks like. To me, this looks like someone took all the symbols in a computer program and decided to organize them by shape. The reason why this program looks so weird is because Forth uses postfix notation. This is like Lisp's weird cousin. This is the way that HP calculators used to work. I think they still work. So all of your operators go after the operands.
Well, we call those.
What does the period do? What do the values do? Good question. Well, we're going to look at that. The first thing that's important is Forth is a stack-based programming language.
Yep.
Everything operates on the stack. And there is effectively, we'll gloss over some things, one stack that you work with. It is the stack. First, we have the number 4, because luckily this program goes left to right, which for my English-speaking brain makes it a lot easier to read. Number 4 isn't just a value. It is also a command. The command 4 takes the number 4 and pushes it to the top of the stack. 5, same thing. It's going to take the number 5, push it to the top of the stack. 2, push it to the top of the stack. Now we have our stack. We then get to the plus operator. The plus operator takes the top 2 items on the stack, whatever they happen to be, pops them off of the stack, adds them together, and pushes the result back onto the top of the stack.
Yeah.
Then we come to the multiplication operator, which again takes the top 2 things off the stack, multiplies them together, pushes the result back onto the top of the stack. Finally, we have the period operator, which goes in and takes whatever's on the top of the stack, pops it off, and then outputs it to standard out or whatever your output stream happens to be. This program doesn't have to be written in this really confusing way. You could also write it this way, which makes a little bit more sense, which is we're going to take 5 and 2 and add them together. We're then going to take the result of that with 4 and multiply it and then output it. It reads a little bit simpler, but I wrote it in the confusing way just to emphasize Forth's postfix syntax. Function definitions in Forth.
Before you move on, if anyone's interested, there is a language these days called Factor, which is also stack-based and looks very much like Forth and is available for Mac and Windows and all those other things if you ever care to play with it. It's kind of
Forth is still used to this day, and there are even there are Forth REPLs online that you can play with. There's also a functional cousin to Forth that I'm hoping to give a talk on later, but that's like a whole other thing, and it's a weird language.
I believe that Apple Bootloader was written in Forth as well.
I wouldn't be surprised. Forth is surprisingly popular in embedded systems, and we'll get to why in a moment. It's not as uncommon as people think. It's just that unless you're doing embedded programming, you're not going to see this type. So, function definition in Forth. This is where Forth gets cool, in my opinion. This is a function definition for a function to square 2 numbers. First, we have the colon. The colon just says whatever appears after me is the definition of a function. The first thing is going to be the name of the function. We're going to call it square, because it's squaring 2 numbers. The next function is dupe. What dupe does is it takes whatever thing happens to be at the top of the stack, and it duplicates it and just pushes that back on the top of the stack. So previously we had 7 at the top of the stack, we're going to duplicate and make 2 7s. Then we call the multiplication operator, takes the top 2 things, multiplies them, and there we go. Then the semicolon just says we're at the end of the function. Now the really cool thing about this, some of you may have noticed, here we have a function definition. We are not defining what the parameters are. We are not defining the input. We don't have a return statement. The reason why is because everything in Forth operates on the stack. You don't need input, you don't need output, because you're just going to take whatever the stack happens to be, and whatever state you happen to leave the stack in is just whatever the next thing we'll use.
Why don't you have a period like you did in the other example?
Because we don't necessarily want to output it. So if we want to square it, we're going to want to leave it at the top of the stack, so then the next thing will have access to it on the top of the stack. If we use the period operator, we would have effectively performed a no-op as far as other functions
This
are
is
concerned.
continuation hashing style.
Yeah.
And you just mentioned to me a little while ago that JavaScript doesn't have arity checking. It's the same thing.
Well, this is different because there's a difference between arity checking and there is no arity. In comments, they will put in the assumed arity, but I mean, this is way slicker. Now, the cool thing about Forth is that it's really simple. All that you have is a stack. You don't deal with local scope or lexical scope or modules or all this complicated stuff that makes an interpreted language hard to implement. The reason why Forth is popular in embedded systems is it is so stupidly easy to implement that you can run an interpreted language that will give you the advantage of having a REPL. It'll be easier to work with and easier to reason about, but you can implement it on these really tiny, simple CPUs. Yep?
What does that do if the stack is empty?
I don't know if there's like an implicit null, and like obviously there's no type, so I haven't dug into Forth, but you know, it's... All right, so Ron Garrett had the advantage that Forth was going to be really simple. So he had a really orthogonal processor, which means writing a compiler for it isn't going to be that bad. And he has to write an interpreter, or has to get that to run in Forth code, and compiling Forth code is not that bad because it's such a stupidly simple language. He had another weapon in his back pocket. This may have been the reason why he was able to do this, and that is Common Lisp. He was a Lisp programmer in the 90s. And Lisp programmers are awesome and do really amazing wizardy things, in my opinion. Let's not get into Lisp though, because that's like a whole other thing, and it's just a bunch of neckbeards, whatever. So, Ron Garrett worked away on the problem. He got help from the magnetometer team. They did help him sort of figure out, okay, how does the magnetometer actually work? What does this code do? Because I don't know if you've ever looked at Forth code from the 1990s. Written by JPL, but it's a little confusing to read. Trust me. And so, using Lisp, he was able to hack together a compiler, and he was able to create a fix, and I believe he did it in like 3 months. And so one person over like, at most 3 months, working away at this as a side project, I mean, that's relatively cheap. So was able to fix the Galileo magnetometer, get it all working by using Common Lisp to write a compiler, interpret the code, get all that stuff working. Luckily, Ron Garrett uploaded his fix to GitHub. So we can see here that first line with the fill exclamation point. That's a function that he rewrote. Then that's the compiled bytecode below it. Then the next thing is another function that he rewrote, and then the compiled bytecode below that. So it was a relatively complicated fix. He had to kind of sort things around. I believe he effectively had to basically just kind of like write a little null thing that filled up that bad part of memory so that, you know, nothing good was there, and then take another function and write it in a more efficient way so it could squeeze down in a smaller space. However, I am not a Forth programmer. I am not familiar with the inner workings of the Galileo magnetometer, and I can't read 1802 machine code. If you can figure out how this works, awesome. It's all available on GitHub. I'd also recommend looking at that because there are some fun, weird things in there and some funny comments. So I contacted Ron Garrett because I had seen a talk by him. I had read some of his articles. He's a really good guy, and I was going to give a talk of this in Major National Conference. So I wanted to ask him, you know, what can you remember this, and are there any lessons that you think we can pull out from it? He said, you know, this was about 25 years ago, and it was one of many side projects on a really big thing, and he did a lot of interesting stuff at JPL, but he didn't remember very much about this because this is a very specific thing. However, he did say that there was one lesson that he thought you could take from it, and that was that Lisp is totally awesome. He's a big Lisp fan. He's done some cool stuff in Lisp. It's worth looking up his other talks and his articles that he's written. Some of it edges more on sort of project management type things, and there's some interesting things to be learned from there. So I definitely recommend looking it up if you're interested in learning more about this stuff. But he barely has anything written on this specific patch. So takeaways from these 4 stories. I don't have too much in the way of takeaways because I think other people should figure out what this stuff means to them. You can learn from this or not learn from this, whatever you want, and take away whatever lessons you want from all of these bugs that have happened. However, I do want to say that one takeaway that I think everyone should have, and this is a theme for most of the talks that I've ever given, is that history is totally awesome. We as programmers do not spend enough time learning from the past. Like, we say that not invented here is a bad thing and we shouldn't do it, but then we go ahead and say any code that was written 5 or 10 years ago is total legacy garbage and there is nothing to learn from that. As opposed to the fact that, hey, maybe these systems that we all hate that have been around for 10, 20, 30 years, maybe there's something there, because how much code have we written that has managed to stand the test of time for multiple decades? And we may think that we know everything now, but a lot of the stuff that we are currently discovering and all of these new languages that we're making may have in the past languages that were very similar. And honestly, a lot of the stuff that we do in functional programming is stuff that was written about in the 1960s or 70s or 80s, or in the case of some things, in the 40s, before they even had computers and the word computer meant something different. There's a lot that we can learn and a lot of stuff that's buried in academic articles and blog posts that people have written. And there's a lot of stuff being lost. So it's nice that some people are writing things down, but we as programmers should spend more time not only learning from the past, but also writing down our experiences and projects that we worked on, things that went well and didn't go well, so that other people can learn from them. If you want to learn more, the Remote Agent Experiment is a talk that Ron Garrett gave at Google. It talks about another project dealing with Lisp at JPL and what went terribly wrong with it and all the issues. It was not Lisp's fault, in his opinion, but also in my opinion. It's a really interesting talk. It talks about some cool stuff. Definitely worth a watch, though. Look, it's not like a big, exciting, flashy talk. Digital Apollo. If you're interested in space and the Apollo program, go ahead and read Digital Apollo. It is about the culture behind the design of the UI and a lot of the Apollo program, because a lot of the Apollo design was not just engineering, it was also dealing with the culture and the psychology of the people operating the rockets. And the UIs were not just trying to get someone to the moon, it was also trying to deal with cantankerous former test pilots and dealing with military culture. And it's a really interesting read if you're not big into the technicals. This is also a good book to read because it doesn't dive too deep. It deals with a lot of the more sort of UX and cultural side of things. However, if you are into the technical side of things, the Apollo 11 source code is available on GitHub because we live in the future, and you can, on GitHub, look at code from the 1960s. This is really cool. There's a lot of fun stuff in there. Some articles have been written about it. However, I don't know about you, but in school and also in life and in my job, people haven't been teaching me how to interpret code for the Apollo guidance computer, a computer that was entirely designed basically from scratch, the Apollo program. But don't worry, there is a book called the Apollo Guidance Computer, written by Frank O'Brien. It is massive. It is hundreds of pages. It will tell you what all the commands in the Apollo Guidance Computer do, how all the bits are arranged, how the architecture of the program was set up, where all the bit masks were set up. It is hundreds of pages of incredibly painful technical detail. The man who wrote it, I don't know why he wrote this thing, but it is an amazing, amazing reference, and I've learned a lot from it, though it is a dense read. Finally, there's a documentary series called Moon Machines, which is people who worked as engineers on various parts of the Apollo program. There's one on the Saturn V rocket, there's one on the Apollo guidance computer, there's one on the spacesuit that they use, and the spacesuits that we still continue to use, which I highly recommend watching because you would not guess what company won the contract for creating the Apollo spacesuits. I guarantee you, you would never guess what the company is and what they are most known for. It's surprising to say the least. Finally, just a couple
Is it a hire company?
Can you skip back for a second? I want to get a picture of that last slide.
I already got it.
Thank you.
And all the slides are up on my GitHub page if anyone wants to see it.
And will be very soon in the GitHub page of the group, right? On the Meetup.
I can share it with people.
Thank you.
Special thanks, since we're way over time. Ron Garrett, just want to send a big shout out to him because he was very nice, responding to an email. Super good guy to talk with. Also my friend Rachel McGuffin, she's the one who did all the illustrations in this.
I was going to ask you.
Yeah, me too.
Because cute animal illustrations make anything better, especially nasty technical stuff. And thanks, everyone. And y'all have any other questions or want to talk? What?
Was that the one?
No, that's other artist.
Did you work or study?
Liz Cleveland.
Liz Cleveland?
She has a Tumblr page. She does really cute cartoons with animals. They're good and uplifting and make you feel nice.
Yeah, I like that.
Did you work or study in aerospace?
Nope.
How'd you get interested in this?
I'm a nerd.
Nerd union.
My degree is in art and science, and I'm sorry, my degree is in art and design and theater.
2 more questions.
And then you can ask me after.
And then after we can stay as long as you want, but 2 more questions.
Or
1 more question.
Or 0.
Yeah. I think 0. We can stay here as long as we want, but we have a couple. Oh, last question.
No, I was just about your friend, the one that drew the pictures.
Mm-hmm.
What was her name?
Rachel McGuffin.
He'll have a link to the slide.
If you are interested in illustrators, both in town and around, I am friends with a lot of illustrators for some reason. So if you ever need illustrations, I can hook you up.